Hello and welcome to this pre-recorded session, Building a Robust and Intelligent Text Similarity Service with BERT. My name is Philipp Eisen, and I work as a machine learning research engineer at Peltarion. Here I mainly work on two things. The first, I help our clients make use of the most recent advanced machine learning techniques, mainly in NLP, to solve their business problems. But I also help internally build our platform, the Peltarion platform, which helps users that are not necessarily data scientists or programmers to get use of machine learning, to make use of machine learning and deep learning algorithms and be able to deploy them into production. Before joining Peltarion, I was working at King, also as a machine learning engineer. And before that, I finished my master's degree in KTH and UPM, University of Politecnica of Madrid. Some personal things to help you remember me better or get to know me better. I really like climbing, skiing, hiking, and of course, building things with machine learning, especially side projects. You can find me on Twitter with this handle at Philipp Eisen if you want to get in touch. So let's get to the topic. What is semantic text similarity? I want to answer this question along an example. Imagine you wake up one morning recently, like I did, to this news headline. Hackers take over prominent Twitter accounts in simultaneous attack. And you think to yourself, okay, wow, that sounds pretty serious. I want to find out more. Let's see what other news outlets say. So you're going to collect some news headlines of the day. So those are actually news headlines of that same day. First one, Twitter hides Donald Trump tweet for glorifying violence. This one is also about Twitter, but not about Twitter getting hacked. So yeah, recently Twitter is a lot in the news, it seems. Then Washington State beat back COVID-19. Now it's rising again. And the last one, major US accounts hacked in Bitcoin scam. So here we can see this is also about Twitter accounts being hacked. So what I mean by when we talk about semantic text similarity, we want our computer or machine to understand that that our query, hackers take over prominent Twitter accounts in simultaneous attack, is actually similar to the most similar to the last one, major US Twitter accounts hacked in Bitcoin scam. So we want to be able for our computer to understand that and rank that. For example, like this. So as you can see, the major US Twitter accounts hacked in Bitcoin scam, as it should, is here being ranked the most similar to the query, hackers take over prominent Twitter accounts in simultaneous attack. The second most similar to the first one talks also about Twitter, but it doesn't talk about some accounts being taken over or hacked. So it's not as similar as the first one. And the last part is talking about Corona, but it's not talking about Twitter or accounts being hacked at all. Another thing what would be nice is if this wouldn't only work in English, but also in other languages that I might be interested in reading about, for example, Spanish and German. So the first one, unos defraudadores hackearon las cuentas de Twitter de figuras famosas. The Spanish one is more or less pretty much saying the same as the query. So this is the most similar to the query. And the German one, Twitter accounts zahlreicher Prominenten wurden offenbar gehackt. This one's also very similar. So the Spanish and the German one are actually more similar than the English one to the query. And in this case, our machine understood that. I will explain how this actually worked, and you will also be able to reproduce this with some code if you want to. So yes, how does it actually work? First of all, like I said, you can reproduce this with this, you can access this Colab here under this link if you want to. and play with semantic similarity in a very basic way yourself. So basically the way it works is we have these input sentences that I was saying before. So those are like the news headlines that we collected. This here is the first one we saw. And we take these news headlines that we collected, and we use a model that can encode these text into a vector, and specifically in a semantically meaningful way. That means that we trained that model should be able to produce these vectors so that they are similar if the text talks about something similar. And that doesn't mean that they necessarily need to use the same words. It's about semantically talking about a similar thing. As you can see, it works with different languages as well. So it's not really relying on the words, but instead it learns from data how the meaning is portrayed. So once we encoded our the news headlines we're interested in searching, let's say that is all the news headlines we collected, we also do the same thing to our query, and then we can see which one is the closest one to our query. And we do that usually through some distance metric. The distance metric, for example, we can use cosine similarity, which is pretty common. So we just calculate the cosine between all these vectors and take the one that is closest to the query and order them in how similar this vector is to each of those vectors. Other distances can be the Euclidean distance, or you can even learn how to calculate the distance. So as you can see here, a lot of the magic happens through the model. And that's pretty important to know. I won't be talking too much in this talk about the model. However, the model is the first thing, and it's a pretty important thing when we talk about semantic similarity. That model is trained, as I slightly mentioned before, to produce semantically meaningful representations from text. And it does that with training data. And there's some data sets that have tasks that require understanding what the meaning of a sentence is or of text is in order to be able to solve the tasks. And we train the model for those the ones that have heard of it usually in a Siamese way or with a triplet loss, because in this way we force the model to represent as much as possible in the embedding representation and not in the output. If you haven't really heard about that, you can read on about that, but it's not necessarily required for the rest of this presentation. But I want to say, like, even if you don't have, you can of course train. You can train this model to actually learn what your definition of similarity is by showing it a lot of examples. Of course, that means that you need to collect a lot of data, but yeah, some of you might have enough data for which it could actually be useful to learn your definition of similarity from data. Otherwise, there's two pretty good pre-trained models that I think are fairly good baseline if you don't have data yet or not at all, or if your problem is like a very general problem. So if your sense of similarity is not very specific to your problem. And one of them is called sentence transformers. That's also what plays into the title. There's also this SentenceBERT model in there. And sentence transformers is based on Hugging Face, on the Hugging Face library, and based on PyTorch. The code is available on GitHub. You can find that if you Google for sentence transformers. And from there, you can download the weights of the model and use it. the pre-trained models. They have different models, some that work with English only, and some, like the one I showed you in the first example, that work across different languages. Then there's also, by Google, Universal Sentence Encoder. That one is TensorFlow based. There's no code available as far as I'm aware, but you can download the model from TF Hub and also use the model like that. This downloading from TF Hub also allows you to fine-tune on your own data, so you don't necessarily have a disadvantage for not having the code, but I guess in the end it depends on which one to use, depends on your preference of maybe PyTorch versus TensorFlow and being able to see the code or not, of course. But both work similarly well as a baseline for semantic similarity, I would say. Okay, now we have the model, but now let's talk about how we actually can build a service for semantic similarity search. We have, as I talked before, we already have the model, and I assume, since we want to be like, I'm assuming that we have some database with some text, because it only makes sense if we have some data that we actually want to query or like find similar things on. And most companies have data in some form of text usually. So basically, what we can do from what we know so far is we have this database of text. We have here one identifier shown by this key and the text entry, and we can send it through the model. And then we keep the key. We just basically pass this through. You can think of it's not really going through the model, but just so you know, like this is basically passing through, and we get the embedding for the text. But then what do we do with that? That's the next question. And a good way of storing this embedding, the naive way of storing these embeddings would just be in NumPy arrays, and then and just going with that. And that works okay if you have small data, but it is better to store those in approximate nearest neighbor search indices. And they allow for fast but approximate retrieval with a lot of data. So you can scale up to millions or maybe even billions of data points and still have a fast retrieval of similar items. And also some of those libraries allow to load the embeddings in a very fast way as well, which you don't necessarily get if you have to load big NumPy arrays. Some examples here as well. There's Fice from Facebook, Scan by Google, which was recently released, and they claim to be beating a lot of benchmarks. There's also Annoy by Spotify. I know about Annoy that they have this memory mapping, so that's like one of the libraries that allows loading of the embeddings really fast. But as always, different libraries make different trade-offs and have different performance benchmarks. And you can check out this GitHub repository by Eric Bernardson, the author of Annoy as well, but also the author of this approximate nearest neighbor benchmarks, where you can compare different nearest neighbor searches and their performance. Some trade-offs you should consider when selecting the library. A very common one is, of course, the queries per second that you can perform versus the recall you get. So you have this trade-off of how fast you get a result and how accurate the result is, basically. And another thing, some of these libraries are allowed to modify the index at runtime, and others don't. So that really depends on how you would want to build your application. If you would want to like continuously add more things to your database, or if let's say a batch job is good enough. So now if we go back to this slide, we now know what we should do with those embeddings that the model produces. We should save them in our ANN index. And that basically concludes the indexing phase. But we also still have to, for our service, we also, that's only part of it, because we also want to actually serve those artifacts that we did in what we call the query phase. So we have here, these are all the same artifacts. So we have this text, this database of the text, with text that we have the model, and we have our approximate nearest neighbor index. So let's say a user comes with a query. We also have to accept this somewhere. So we have to build some sort of small API layer. And that user now sends us a query with some text, as shown by this icon. Our API then forwards this text to the model, which encodes it into this vector that we saw before. And we use then that vector to query the index to get back the keys, the keys to the most similar vectors that we stored before. We can then use that key to get the original text from our database where we stored our text before. So now we have the text, and or the texts, which is the, like top n, however many the user requested, and we can then return those to the user. So this is basically now the logic part of the model, and I will make some suggestions of how you could, for example, how you could actually implement this and deploy it. Of course, those are only suggestions, and there's a lot of opinions among different people. But one way could be that you have this first part being a Kubernetes job, if you are familiar with Kubernetes and like that. So you could have it check that if your text or like your data has changed, and if it has, you would rebuild the index and produce this an index artifact for the particular database you have on a very high level. And those services all could be Kubernetes deployments, so that you can scale them independently. Especially the model could be a bottleneck if you get a lot of requests, because it's very intensive on compute. So you could have, for example, an autoscaler on the model and scale that independently from the other parts, which might not necessarily be as intensive, resource intensive as this part. I intentionally left out the database from this part, because usually I prefer to have databases in a managed database service, but it really depends how you want to deal with your data, and maybe also already where you stored your data before. So this basically is all I have for explaining the architecture of how to build a semantic similarity service. And I have some demos that use this, and I'm going to show two of them to you now. The first one is you can find it at textsimilarity.demo.peltarion.com. Basically, this is a front end that serves on the back end something very similar to what I presented in this presentation. And there's two data sets indexed. One of them is hundreds of millions of Quora questions, and the other one is titles of patent applications. So, for example, if we search Twitter here on the Quora index, you can see, do you use Twitter? What is Twitter? Who is viewing Twitter? So, like on Quora, there's of course a lot of questions about Twitter, so you will find questions about Twitter. But what I find interesting is, and I think it's interesting also to show how the model is encoding the similarities. If you search for that in the patents dataset, where no one is actually using the word Twitter, but you can find like the most similar patent applications are social networking web page application, social network service, and things about social media. So this is like one demo where you can see how it's where you can play around with it a little bit and get a feeling of how it works. Another demo I built with a colleague at Peltarion was also basically to find out to learn more about actually how the similarity search works, or how it performs in the wild, so to say. And this one takes the, for the ones of you who are aware of Hacker News, this is the Hacker News news feed. Hacker News is like a news aggregator for news in text, for those of you that don't know. And basically what it does is it takes the current Hacker News front page news article titles and finds the most similar ones between 2006 and 2015. And I found this a pretty fun side project to do and to try out. I think also it's a kind of fun demo to see, because sometimes you see like pretty interesting things reappear over the time. To the presentation. Those both those demos are available publicly, so you can easily try it out for yourself. And then there's also that's not only fun in games, but I want to highlight also one real-world application I've been working on at Peltarion with our together with Ipsos. Ipsos is the world's third largest market research company and operates in over 90 markets in the world. And together with them, we helped them on a product they do, which is the self-service survey creator or editor, and their semantic similarity service was used to suggest improved wording of questions and suggest you some answers that you could add to answer alternatives that you could add to questions that you're asking, but also to improve the recommendations for a next question to ask. So there's actually quite a lot of, you will find there's quite a lot of real world use cases where it's very good and useful to have a sense of similarity between things. So this marks the end of my presentation. Thank you very much. If you want to stay in touch, you can reach me on Twitter on the handle Phil Eisen. At Peltarion, we also have a mentorship program. So if you think you have some ideas about something you would want to solve with machine learning, but are stuck and need some help from some people that have been working a lot in the industry, reach out to us under this link. And also, please check out the Peltarion platform and see if you will find something interesting there. Thanks for your attention.